This is our second video on magnetism, and in the first video we went through a lot of theory on right-hand rule and introduction to magnets and magnetism. And in this video I want to use the formulas that we learned in the first video, or we saw in the first video, to use some of the questions that we didn't get a chance to do in the first video. So let's look at some of the questions. So here's the first question. A long straight wire carries a current of 5 amps. So I have the current of 5 amps. At one instant, a proton 4 millimeters from the wire travels at the velocity of 1.5 10 to the third meters per second, parallel to the wire and in the same direction as the current. Figure out the magnitude and the direction of the magnetic field created by the wire. So in this formula, the one that we saw in the previous video, I can calculate the magnetic field at the point where the proton is. So I need mu, which is permeability of the free space constant. So that's 4 pi 10 to negative 7 Tesla meters per amp. And divide by 2 pi. Or I can replace mu over 2 pi with k, which is 10 to the negative 7 Tesla meters per amp. And then I have the current and divide by the distance. So if I want to calculate the magnetic field away from the wire with the current, I have k, and I have I, and the distance. So k is 2 10 to the negative 7. Current is 5 and the distance is 4 millimeters, so that is 10 to the negative 3. So I can cancel negative 3 from the top and the bottom, so negative 3 from here and negative 3 from there. And also I can 2 over 4 gives me 2 with the denominator. So I have 2.5 10 to the negative 4 Teslas. Now, to figure out the direction of the current, of the magnetic field around the wire with the current, I have to place my right-hand rule. So my thumb is going to be directed in the direction of the current, and then I'm going to wrap my fingers in this direction, like this. So looks like the magnetic field around the wire is going to go in this direction. So that means on the left side of the wire, the magnetic field is coming at me, and on the right side of the wire, the magnetic field goes away from me. So now I have a proton, a positively charged particle. So I have the magnetic field on the right side like this, moving away from me. And then I have a proton, a positively charged particle, is moving in this direction. So here is the velocity. Now I want to find the force acting on the wire and the direction of the force acting on the wire. And again, I have to use right-hand rule, but in this case it's a different right-hand rule. It's for the proton. So here I have different right-hand rules, and the one that I'm going to be using is the second one. So I have the magnetic field lines going away from me on the right side of the wire, and the way I drew the picture in the different page. And then I have a proton, positively charged, moving in this direction. So now I have to place my hand, so the direction of the magnetic field, aligned with your fingers. And then the direction of the proton, the velocity of the proton, is going to be aligned with your thumb. So try to place your hand where you have your fingers pointing into the page of the screen, and the direction of the thumb is showing the direction of the proton. So it's going to look something like this. Your fingers are away from you into the page, and your thumb is pointing up. So the force, so I have here, there should be right angle here. So the force, the velocity is in this direction. The magnetic field lines away into the page, And the force that is acting on the proton is out of your palm. So the force acting on the proton is going to be to the right here. So I try to do my three-dimensional hand, but it's going to be perpendicular to the page with your fingers perpendicular to the page, and the thumb is perpendicular to your fingers, and the force is going to be to the right. Now I have to calculate this force. And to calculate this force, I will need a different formula. I will need the formula of the force acting on the charge when it's moving at certain velocity. So I have QVB sine theta, and angle is between the velocity and the magnetic field lines, which is 90 degrees. So if I want to calculate the force acting on the proton, I have Q, V, B, and then I have sine of 90 degrees in this case. So the force is equal to, the charge of the proton is 1.6 10 to the negative 19. It's usually given for you in the AP exam. The velocity is 1.5 10 to the third. And we calculated that the magnetic field is 2.5 10 to the negative 4. And sine of 90 degrees is 1. So now if I plug in all these numbers, I should get something like 6 10 to the negative 20 newtons, and the direction is left. And in the previous calculations, when we did the magnetic field, it is on the right side into the page. On the side where the proton is. In this question, they say that an electron is moving as shown in the figure with the speed of, so we have the velocity of the electron, and it is electron, in the uniform magnetic field of 0.2 Tesla. Find the magnitude of the magnetic force exerted on the electron. So because the electron is traveling perpendicular to the magnetic field lines, I will have the sine of 90 degrees in my formula. So then I have electron, the charge is 1.6 10 to the negative 19. The velocity of the electron is 2 10 to the 5th. And the magnetic field is 0.2. And sine of 90 is 1. So if I plug in all these numbers, I will get the force, or the magnitude of the force. Magnitude means the strength of the force, equal to 6.4 10 to the negative 15 newtons. So that is the force acting on the electron and by magnetic field. And then if I want to figure out the direction at which this force is acting, so if I want to see in what direction the force is going to be acting, again, I'm going to use the right-hand rule. And in this case, I have the magnetic field lines coming at me. So they're coming out of the page toward me. And the electron is moving in this direction. So I have to place my right hand the way to show that my fingers are pointing toward me right now, and the direction of the velocity, which is my thumb, is pointing in the direction of the red line or the arrow. Then in this case, I will get the force acting by the magnetic field on the electron is going to be in this direction. So here is going to be the force perpendicular. And I determine this force by placing my fingers pointing toward me, or coming out of the page toward me, and my thumb is pointing the direction of the velocity. And because it is an electron, it's a negatively charged particle, then the force is acting not out of the palm, the force is acting in the opposite direction. And this is how I see the force is acting in the direction of the purple line. And then sketch the circular motion of the path and find its radius. So if the force is acting in this direction, in the purple arrow direction, then electron is going to switch its direction when in the direction of the force acting. So now, because the force is acting on the electron in this direction, then the velocity is going to change in this direction. And so because the velocity is changing in this direction, now I have to turn my hand, so I still have my fingers pointing at me, and my thumb is pointing with the direction of the red line, because that's where the velocity, new velocity is. Then I will see that the new force is going to be acting in this way. So it looks like the electron is going to be moving in this direction. So no matter where the electron is, its velocity is going to be in the circular motion. So the electron is going to be starting to move in that direction, because the velocity is always going to change, because the force is always changing the direction of the motion of the electron. So I have circular motion of the electron in this dotted direction. When they say calculate the radius, then I see that the electron is going to be moving in circular motion, so I know the centripetal force is going to be present. And in this case, if you remember from AP Physics 1, the centripetal forces can be different types of forces, and in this case your centripetal force is the magnetic field force, so I'm going to say it's the force that is magnetic field force. Then centripetal force is mv squared over r, and the magnetic field force we just calculated is equal to 6.4 10 to the negative 15. Or you could avoid plugging in the numbers if you wanted to do just the variables. So I have this is equal to QVB. I don't have to keep the sine theta because it's 90 degrees again. Then one of the velocities is going to be cancelled. And if I solve for the radius, this formula is not given, but you will see this type of questions on AP exam. So the radius is going to be equal to mv, the mass of the electron, velocity of the electron, divided by q times b. So I could use this formula to calculate the radius, or I can just calculate the radius by plugging in the numbers. So I will have the radius is equal to the mass of the electron, which is 9, 11, 10 to the negative 31st. The velocity of the electron squared, which is 2, 10 to the 5th, all of it squared, and divided by the force of the magnetic field that I calculated is 6.4, 10 to the negative 15. So I get the radius of the curvature for the electron when it's rotating is equal to 5.7, 10 to the negative 6 meters. In the last question, they ask how long will it take for the electron to complete one revolution. So you have that the velocity is equal to the distance over time. To find the time, you need the distance over the velocity of the electron. The distance the electron moves around the revolution is equal to 2 pi r, the circumference of the circular motion that electron completes, and the velocity of the electron is given. So if I plug in my numbers, I will get 1.8, 10 to the negative 10, negative 10 seconds. For the next question, we have a straight segment of wire 50 centimeters long. So I'm going to underline everything that is given since I don't have much space to write that I could do in the classroom, everything that is given. So the segment of wire is 50 centimeters long with a mass of 30 gram, that's 0.03 kilogram, is positioned horizontally in a uniform magnetic field of 0.025 Tesla, so that the current moves perpendicular to the field, depicted into the paper as shown. So we have the wire and the magnetic field into the paper. What current, magnitude, and direction will be established in the wire so that the magnetic field just counterbalances the weight of the wire? So when I have the forces acting on the wire, at first I need the direction. So the force of gravity is going to be, let me just redraw the wire. So here is my wire. And the force of gravity is going to be acting down. Then the force of the magnetic field needs to be acting up. And that is equal to I, L, B, and sine theta. In order to determine the direction of the current, so I know this is not the magnetic field created by the wire. This is the magnetic field that the wire is placed into. That's a foreign magnetic field lines. So the wire is placed in the magnetic field. And the length of it is 50 centimeters that is in the magnetic field. So in order to determine the force that is going to be acting up, I need to place again my right hand. And my right hand has to be, my fingers have to be pointing away from me. So my fingers have to be pointing in the direction away from me toward the page. The force acting has to be out of the palm. So from my palm, I have to have the force, the magnetic field force. And that means my thumb has to be pointed in this direction. So my fingers are going to be into the page. The force is out of my palm. And the current needs to be in that direction. So here is the current. So to calculate the current needed to counterbalance the gravitational field force to cause the magnetic field force, I have to set these two guys equal to each other. So I have ILB, this force, magnetic field force, sine of 90 degrees. So I'm going to skip that part, is equal to mg. So I is going to be equal to mg divided by LB. The mass is 30 grams, so that's 30 10 to the negative 3 kilogram. And g, acceleration due to gravity, is 10. The length of the wire that is in the magnetic field is 0.5 meters. And the magnetic field is 0.025 Tesla. So I is going to be equal to 24 amps. There are a few questions that I found in the study guide for AP Physics 2, and I just wanted you to see that a lot of AP questions, multiple choice especially on AP exam, are going to be formula related. And in this question they say that a mass spectrometer is designed such that the electric field strength in the velocity selector proton of the tool is E, and the magnetic field strength in both the velocity spectra and the deflection region is B. What is the radius of the path of the slightly charged positive ion of mass m? And the mass spectrometry is an analytical technique that measures the mass to charge ratio of ions, and the results are typically presented in as mass spectrum, or they plot the intensity as a function of mass to charge ratio. Khan Academy has a good lesson on mass spectrometry, and so I'm just going to go over this very quickly so you understand how it works. So they take ionized gas, and then they use ion accelerated part of the spectrometry. They use electric field to accelerate, and after the ions accelerated, they have momentum, they have the mass, and they have velocity. So then they use magnetic field to deflect the ions, And because the ions are positively charged, that ions means there's no electrons, it's only the positive charged part is left. And so when you deflect it with the magnetic field, the force that you have to apply to deflect the charges is proportional to the charge of those ions. And this is where the mass over charge part comes out. So by the force that you need to apply, at first the force that you need to apply to accelerate the ions, this is when you that force is related to the mass, so it's the electric field accelerator. And then the magnetic field deflector is the one that will be dependent on the charge. And then when you have those two, the force, electric field force and the magnetic field force, and then you can calculate the mass over charge proportion. So because there is that deflector that makes the ions move in a circular motion when they rotate or turn, then I have to set up centripetal force is equal to the magnetic field force. Then I have mv squared over r and equals to qvb and sine theta. And if sine theta is 90 degrees, that is the motion of the ions perpendicular to the magnetic field lines. Then I can solve for the radius, which is going to be mv squared divided by qvb, but and equals to mv over qb if we cancel two v's, one in the numerator and the other one in the denominator. And when there is electric field force is acting on the particle to accelerate it, we have the force that is acting on the particle is equal to Q times E, where electric field, and then there's going to be the magnetic field force involved to turn that particle, the ions, QVB. And if Q and Q cancels, then I have the velocity has the relationship between E and B. So there can be a relationship between E and B, and I can plug it in into my formula because I know that the velocity depends on the magnetic field and the electric field. So that will give me m and q b squared and e over b squared instead of the velocity. So instead of the velocity, I'm gonna have e divided by b, but I already have 1b in the denominator, so that will give me b squared. And from here you see that D is an answer. So a lot of AP questions are going to be formula related, not the numbers, especially multiple choice. Here I have a next question that I found also for the study guide for AP Physics 2. A particle of given charge and velocity is situated in a uniform magnetic field as shown in the following scenarios. Rank the magnitude of the magnetic force on the particles from greatest to the least. So the force acting on the particle by the magnetic field is equal to Q VB sine theta. And we're going to be using this formula for every single particle in A, B, C, and D, E, and F. So here I use the formula QVB sine theta, and in in A, B, and D, the velocity is equal to 0. So in every single one of these ones, the velocity is equal to 0. So that's why I'm going to have the force acting on the particle is equal to 0. So here I have 0 newtons. And in E and F, the particle is moving parallel to the lines. It's not perpendicular, so you have sine of 0 degrees in each. So that's why you have, again, 0 newtons acting on the particle. So the only force that is actually acting on the particle is in C. So you have Q, which is 1 coulomb, velocity, which is 1, and the magnetic field is 1. So you have 1 Newton. So they ask you to rank the magnitude of the magnetic force on the particles from greatest to the lowest. So the greatest is going to be at C, and then for the rest of them, the force is equal to 0 newtons. So the force is the greatest in C. Here is another question that they ask you, and they say in the scenarios below, the charged particle is deflected in a circular path as it enters a region of uniform magnetic field. For each scenario, determine the direction of the magnetic field. My next video, number 3 for magnetism, I'm going to do all right-hand rules. So if you do not understand right-hand rules or are still confused about it, the next video is the best one to watch. And then you can come back to look at this question one more time when you understand it better. So in order for the positive charge to move in the circular motion in A, then the velocity has to be forward and to the right, and then force needs to be pointing down in order for the particle to make motion down. So I have to place my hand, so my thumb, right hand thumb, is pointing the direction of the velocity, and the force is coming out of my palm. So which way should be the magnetic field in this case? So if my thumb is pointing to the right, and my and the force is coming out of my palm, that means the fingers need to be pointed toward me. If the fingers are pointing toward me, that means the magnetic field lines are coming toward me. So the direction of the magnetic field lines in A would be toward you. For the second one, the positive charge is coming in this direction, but the force is acting on it is in this direction in order for it to start moving in the circular motion as shown. So in this case, I have to point my right hand thumb with the direction of the velocity, and the force must be to the right. So I need to position my hand, right hand, flat hand, where my velocity is thumb up, and then the force acting out of my palm is to the right. And that is again, the magnetic field lines are going to be coming out of the page or toward me. So my fingers will be pointing toward me. So try to position the hand where the fingers are pointing toward you. The force coming out of your palm to the right, and the thumb is pointing up with the velocity. For the next particle, there's no force acting on it in C. That means the particle is parallel to the magnetic field lines. So the magnetic field lines either pointing down in this case or up. It doesn't matter. So it can be up or down. For the next one, it's a negative charge. So it's not out of my palm. It's going to be in the opposite direction. So the force is acting down, and the velocity is in the direction to the left. So now I have to position my right hand where the force is coming out of the other side of my palm down, and the velocity is to the right. My thumb is to the right. And that will happen when my fingers are pointing toward me. So you have to place fingers toward you, right hand thumb to the left, and then the force is going to be coming on the opposite side of your palm down. So the force, the other side of the palm, the hand has to be facing down. For the next question, I have the velocity in this direction, the force in this direction. So in this case, my fingers need to be into the page. It's a negative charge, it's a positive charge in this case, it's a positive charge. And so if my fingers are into the page, and my thumb is to the right hand thumb to the right, the force is going to be pointing up. And for the last one, again, this is the velocity, this is the force, and it's a negative charge. So negative charge means the opposite side of my palm. And in this case, again, I'm going to have the magnetic fields out of the page. So my fingers have to be pointing toward me. The velocity, the thumb is down, and the force is out of the other side of my palm. I will stop here. Thank you for watching this video. See you in the next one.